I'm a climate scientist, a professor at Victoria University, and I'm part of this thing called the World Climate Research Program. I'm part of the joint scientific committee that helps guide the program, and my boss is here in town, Professor Detlef Stammer, who chairs that committee. Very lucky to have him here. The World Climate Research Program, as you will hear, really does coordinate internationally all the climate science that feeds the IPCC reports. So it plays a very important role, perhaps doesn't always get the recognition for the role it plays. We always hear IPCC, IPCC. But it's the work of these scientists coordinated by the World Climate Research Program that really is the engine room. So I'll let Detlef explain to you how that works and some of the big issues and priorities that we are grappling with at an international level, that society is saying, we need clearer science on this. Because Detlef's here, he's tired, he's been here, well, he's jet-lagged, but I know him well, he's very stoic, but he's been in I brought him straight into a workshop, so he's been in a national workshop with Sir Peter Gluckman and some of our leaders in sort of climate change funding, stakeholders, the Ministry for the Environment, the Climate Commission. So it's been wonderful to have Detlef here because it's been a catalyst for us to sort of get our national conversation up a bit more. It's starting to fall off for various reasons. I think we know what some of those might be. But we really are in this decade of decisions. We've got to act now. And so you're going to hear about the international perspective, and much of that is relevant to us because it's affecting us, but there's also a local context, and Detlef's been helping us with those discussions today. Detlef Stammer, already said, chair of the World Climate Research Program. He's on the International Science Council. He's a fellow of the International Science Council. He's a renowned physical oceanographer, climate scientist, and he currently is a professor at the University of Hamburg. And I won't fill up all your time, Detlef, with rattling off your CV, but it's very impressive. Detlef, welcome.
Well, thank you very much, Tim, and thanks for the invitation to speak here tonight. And I'm really honored to have been part of the workshop earlier today, and then, in fact, also giving this public lecture. The idea was really, and still is, that I introduce to all the people who don't know about the World Climate Research Program what we are, what we do. And as Tim already introduced you, there are usually actually acronyms, and a lot of our talks are too much acronyms. And so I just want to repeat again that I'm a chair of what's called the Joint Scientific Committee, and that's called the Joint Scientific Committee because the World Climate Research Program is really sponsored or has parents by three organizations. One is the World Meteorological Organization. The other one is the International Science Council, used to be ICSU in the past, and then the Intergovernmental Oceanographic Commission, which is from UNESCO. And these three programs, to some extent, you can think of the World Climate Research Program as being actually a UN-sponsored program for climate research. Now, before I click actually to the next slide, I have to warn you, the transition from my computer to this computer didn't like all the fonts I had, and so I need to read this, I guess. So the goal really, as I said, was to inform you about the World Climate Research Program and its new science direction. But before I get into this, really informing you about the World Climate Research Program, you probably have to hear a little bit about the past. And so we are now older than 40 years. In fact, the World Climate Research Program was founded in 1980 after the first climate conference, UN climate conference, and so it is active since 1980. And what you see here are many of the activities that started since the foundation, but also a couple of other things. For instance, the first of all what we do, but then there is the IPCC activities that started along with or in parallel to what we did. And the IPCC stands for the Intergovernmental Panel for Climate Change. That's actually a political panel that has the charge from the nations to actually assess the knowledge about climate change. As you can see, the first assessment from the Intergovernmental Panel for Climate Change was in 1990, and before WCRP already started with work, was producing knowledge about the climate system and its changes. And it was doing this by, for instance, and I will get to more details, developing an infrastructure, and the infrastructure started with, in fact, gathering climate information. So you need a climate observing system to do so, and that is ocean observations and atmospheric observations. And the climate system, as you will know, it's not just the atmosphere. Typically, people think climate atmosphere. Now, the climate actually has the atmosphere, the ocean, the cryosphere, the land surface, many things. And so you really have to observe things in all these. So developing this infrastructure, WCRP was very essential to do so. And along with this, actually developing climate models. Mind you, we started in 1980. If you think back, what kind of computer did you have at home in 1980? Not much of a computer. And so this is actually, along with the development of the science, came also a lot of technology in development. We didn't have much transistors. So when I started my study, physical oceanography, I am one of the few people who really started physical oceanography from the beginning. We didn't have electronic instruments. We actually had mechanical instruments to measure. And so I think one has to consider this along with the science development since the 1980 went along very closely with the technology development. And that also relates to computers. So the climate models became better and better and better. The better the computers were, the bigger the computers were. We're still actually one of the biggest users of computers and dedicated computers for climate research. And with these computers, we actually now 7 times do climate projections, where we use climate forcing, we use the solar forcing, we use all the changes in the forcing to simulate the past climate system, compare this with our observations to actually test our models, and then go into the future. And through these things, we're able to identify climate variability, the predictability, but also the impact of humans on the climate system. So it's really through all these together that the WCRP, the World Climate Research Program, really provided the information that led to the conclusion that humans impacted or impact climate and will do so in the future. And so that the mark 2015 was really the one where, first of all, the IPCC concluded before that it's very clear that humans impact climate. In 2015 at the COP21 in Paris, the nations agreed to this and came up with the conclusions that we need to do something. So 2015 was a landmark in this sense. There was the Paris Agreement, but there were also different things like the conference on disaster risk reduction, but also the agenda for the 20 goals to prevent poverty and hunger and so forth around the world. That was all kind of around 2015, and it was very clear that first of all we have to do something, but the understanding and quantifying weather and climate risks are really at the core of reaching what was decided in 2015 for risk reduction, for understanding the impact on poverty, on hunger, on improved health and so forth, and also on reducing the temperatures of the warming that at the Paris Agreement was, first of all, limited to 2 degrees, but then actually was, well, I guess the statement was or better. 2 degrees was kind of the limit that was decided on, or better, and then that's where the 1.5 degree goal came from. By the way, the reduction to 1.5 was really enforced by the small island states because of sea level rise. And that goal is out there. It is very much dependent on how we actually reduce emissions. And that also did then actually lead to WCRP to rethink its goals and redefine its goals. I will jump over this slide because I will get back to this, but essentially we are, and we have to realize that we are in a state of crisis, and we are the world, leading to cascading systemic risk and increasing inequalities around the world. We know that human-induced changes have already led to profound changes, atmosphere, ocean, cryosphere, biosphere, and we also know that the last decades, one after the other, were the warmest in history from our measurements. So human-induced changes have led already to significant warming, and we also now are very close to the 1.5. So it's not a long-term goal. We are very close, and we know if we actually continue the emissions as we do, we will probably reach more kind of 3 degrees. Certainly 2 degrees will be hard, and so actually any holding of the warming requires a society with net zero emission. And the quicker we are, the lower the temperature will be. The longer we wait, the higher temperature it will be. So, but whatever, the future society has to be a net zero emission society. But with what the changes that we already see, the probability is really rising for complex and compound extremes. It's really the cumulative emissions of CO2 that leads to this warming, and the reason I can get into this, but essentially the emissions that we do will not just disappear. They will stay in the system for a long time, and they lead to a warming. And then you have many other effects that also lead to extra warming, including water vapor. It's actually water vapor is a very strong climate constituent in the system, but it's triggered by the CO2 and the warming. And if we want to stop it, we really need to respond as a society, and really coming down to a society of net zero emissions. And I think we have to realize that choices and actions that we decide today will have a very long impact. So in some sense, what one actually can say from the knowledge we have is that the past emissions did lead to the temperature rise that we have so far. Our emissions now and in the future will lead to the extra warming. So the quicker we are, the lower will be the limit. Now, WCRP really responded to this. First of all, the WCRP, the World Climate Research Program, it leads the climate research around the world. And so it's really meant to coordinate and identify the big climate questions and coordinate the science. But the big is the big and world is the important part. We do this around the world with ideally really all nations involved around the world, focusing on the big issues. It's not that important that we organize what I do at home. It's not the micromanagement. It's really identifying the big things. And that's, as I said, the infrastructure, the modeling, building, the identifying the next questions, and that's really the mission. We coordinate and facilitate international climate research to develop, share, and apply the climate knowledge that contributes to social well-being. Now, as Tim already alluded to, often this role is being given to IPCC and has a very big visibility for good reasons. But IPCC as an activity is really an assessment activity. It's really taking the existing literature to assess our state of knowledge and not to produce it. And so really the production comes through WCRP, but we also should acknowledge WCRP is not the only activity, the only coordination. We have also something that's called Future Earth nowadays that has a lot of biological, geochemical, and social sciences. And we basically have to consider ourselves a family of climate activities, and we work together. With WCRP mostly focusing on the physical aspects of the climate system and its changes, and Future is more or less working also on the social sciences, but it has the carbon activities, it has health activities, it has other activities under its umbrella, and we have really a very close connection. But I will speak here about the World Climate Research Program today, but we should really think also with the goals I will and the frontiers I will present to you. We have to do this together to reach the goal that are necessary to reach within the next decade or two. Now, the science objective, initially WCRP was created to identify climate variability and predictability and identify really the impact of humans on climate. The new goals are fundamental climate understanding. That's objective number one. We have a lot of insight now, but we have to expand it. We are not done. We have enough knowledge to really say that humans are impacting climate, but for instance, how this works on the local scale, how the regional pattern will change, how water will change. There are really many things where we have to do a lot of science, and this also relates to the objective 2 and 3, which really comes into predictions, predictability of climate over the next 10 years, very important for decision makers. 10 to 50 years. That's actually the realm where, for instance, first of all, governments can do something, but where the adjustment of new structures. I mean, if you want to build a harbor or if you want to build seawall, this is where your investment cycles is. So having these short-term predictions and also the risk that might come is very important for decision makers. The long term is more kind of in 100 years. What will be our climate in 100 years for our children, children's children? And so what is to be expected? Initially, we actually always sort of did this projection end of the 21st century. We are coming closer to this now. Every 10 years, we are coming more close to the end of the century. But now we actually talk about 2300 and so forth. So really the longer term adjustments. And finally, bridging climate science and society. We actually had this also in the workshop today. We really have to develop actionable climate science, and really something that where decision makers can actually build on and make decisions, and translating what Tim and I typically talk about in the coffee break about what we need to do next or how our sea level projections are, translating this into somebody for somebody who builds a harbor and is more interested what's the high level, what's really the highest level sea level. What's the highest risk sea level adjustment I need to do? That's another step, and really doing this is a very important part of climate science, where the usual scientist is not being trained to, but we have to really adopt, and that's where what we also call co-design, really with the practitioners, with the stakeholders, whatever stakeholder means. That's actually where there's also quite ambiguous, but really the politicians, the people who make decisions, or the investments, or society. Really, society needs to understand what's coming to also adjust themselves. I mean, basically, we cannot just point to politicians. We all have to change our lifestyle if we want to come to a net zero emission society. Now, there's really the infrastructure building coming along with this observing system. We really need to identify the observing system for the future, the modeling. So the infrastructure building is a strong part of what a program like the World Climate Research Program is involved. Now, if it comes to the big topics that we deal with, and so I'm not going into all the details, but these are kind of the big ticket items: climate information, predicting the Earth system changes, climate observations and modeling, tipping points. I mean, these are tipping points are things where a climate system might go from one state into something else and not return. And one of the tipping points is, for instance, if the Atlantic circulation suddenly completely changes, switching off some parts, we call this a meridional or returning circulation that carries a lot of energy and heat into the northern hemisphere. If that suddenly switches off, we get into a completely different state. If Greenland comes lower, or the temperature rises to a certain level, we will lose all Greenland ice. We know this, and that would actually be a point where all the ice will go and will not grow back. These are tipping points, and so really understanding when these will happen is something we have to deal with. Climate intervention is really what people think or used to talk about is geoengineering. How can we actually, from an engineering point of view, do something like pulling out CO2 and pumping it into the deep ocean, or pumping it back into the ground? Or a new aspect of climate intervention is, can we actually put stuff into the stratosphere, white material that reflects the sunlight, that we don't get so much sun? And in some sense, some of these activities are meant to reduce the warming, but in some sense is also, well, maybe then we can continue living as we do by stopping the warming, and that is also not really a solution, because the CO2 level will keep increasing, and so we really have to think about the risks with all these. And these are the big things that we deal with, and so there's a lot of science going along with this. There's a lot of organizational aspects going along with this, and I'm not getting too much in the details. I mean, it's just sort of informing you that we, as a World Climate Research Program, we have a complete science and implementation plan, and I mention this only for the younger generation in this room. If you want to get involved and you really want to know what we do, I'm looking for the younger generation as well. That's all described here. But what I do want to explain a little bit, if you do these kind of activities around the world, there's a structure required. And we structure this in what we call core projects, where you cannot read it, but the first line, and I will get back to this in more detail, is atmospheric process, cryospheric process, the ocean activities, and the variability of the coupled system, Earth system modeling, and then global energy and water exchanges, GWEX. These are all programs, and the lower one, regional information for society, where whole or communities are working in, and so these are communities, like all the oceanographers are sitting in what we call CLIVAR, the Climate Ocean and Variability Project, or the cryospheric community working in what we call CLIC, where you work with ice sheets or understanding the processes in ice sheets or high mountains or glaciers and so forth. So this is actually sort of stratified in some ways, but you bring together communities to work together. And at the end, you want to bring it together because we deal with the climate system. It's a coupled system that we really have to understand together. But we actually see these as homes for these communities to working together. And then we have something that is called lighthouse activities, where these communities come together and work on specific aspects where we know we have to make progress and understand something. And the green part you can think of, and I will get also in details here, a little bit like big experiments that you have to do together. It is not a 100-year experiment, but you can think of 5-year experiment to come to results and then move on. And so this is how we organize ourselves. And just a little bit more information for these core projects. It's really hopes. It's enduring hopes for expertise and communities where some people really live in for some time. And for instance, the CLIVAR is really the climate and ocean variability, predictability. These are communities that deal with the ocean circulation. These are communities that also work on the observing system in the Indian Ocean or the Pacific or Atlantic and so forth. So it's really, they really work on many aspects of climate research, or GWEX, the global energy and water exchanges. They work on the interaction of land surface with the atmosphere. How do you, if you change land surface coverage, how the radiation processes change, or how the water cycle is changing and so forth. So they're really expertise in all these boxes that we require to deal with the entire system. And we bring this together, and then the ESMO, it's the Earth System Modeling activity, where even people knowledgeable about the codes, the coding, or supercomputers with the new technology. I mean, this is actually constantly changing. We have to bring our codes onto the new hardware. There's also the climate CMIP. We call this the CMIP, the Coupled Model Intercomparison Project. The activity that provides the projections of the climate system, which is the basis for the IPCC assessments. So these are all activities we have in these co-projects, and then we have. I really want to highlight this. And again, there's a font problem from one computer to the other. But these are really New Zealand scientists, experts involved in all these core projects. We have Tim Nash here in the JSC and the highest level organization aspects, can go back here. It's a joint scientific committee on top. It's really managing the entire World Climate Research Program. Tim is part of this, but we have here all these younger scientists. It's all right? It holds for me as well. Really active, and you basically see, for instance, Erik Behrens is in the explaining and predicting the Earth system lighthouse activity, and I will get back to this. We have Luke Harrington, Olaf Morgenstern leading the APARC, the atmospheric processes. It goes through, we have Natalie Robinson in CLIVAR, Inga Smith in CLIVAR, and then Lauren Vargo in CLIC. So really, New Zealand is really present in all these, that's why it's so nice to also be here and talk to these communities. Now, coming back to these lighthouse activities, these are really organized to make progress with respect to questions where we really know we need to progress if we want to be better in the prediction or better in advising or designing climate information. And we have, in fact, now 6 of these lighthouse activities. They are really limited time activities to make progress. And the top one, explaining and predicting the climate changes, is really about expanding our basic knowledge on very specific parts of the changes. We have the My Climate Risk is a framework to understanding the risks that come along with the climate changes over the next 10 years. So really better understanding how is that risk affecting societies, and each community is different. It's more susceptible to climate change, and the risk, you cannot define one global risk. It really concerns South America has a different risk than Africa, than Asia, and we really have to deal with this on a local basis. And the safe landing is more the long-term changes. So that's the 100-year to 300 years. Sea level changes is part of this, for instance, but other aspects, carbon sequestration, water changes, many things. And then on the other side, we have what's called digital Earth. It's really the concept of digital twins, which you might know from the industry, where you have a car and you basically develop, or a spacecraft, and you develop the same thing in a digital way on a computer that you can manipulate it and see what if. I mean, if my car has a flat tire, what happens with it? And so the idea is now develop really a digital twin for the Earth system, where we can really play around and understand if we make these changes, what happens afterwards, including if we want to do, or if we do solar radiation management, do we actually move into what's called a snowball Earth, a situation of the Earth that actually happened in the history of the Earth, where the entire Earth did freeze. We actually had the Earth in the history, a period where the Earth was entirely frozen. And if we start to manipulate the solar radiation, we definitely want to make sure that this will not happen, or other things. So this is where we have a system that also would, for instance, include the coastal parts. If we have sea level rise, how is my coastal system affected by sea level rise? And so these are really things you don't want to wait so long until it happens. You want to understand this before. So that's Digital Earth. GFEX, it's in short way for the Global Precipitation Experiment. It's actually one of these global experiments where we first of all want to improve our knowledge about precipitation, improve the models in predicting precipitation. And then from there, we want to actually go into the question, that sort of the end-to-end water question. How much precipitation do you get? How much evaporation do you have? How much water is at the end available for irrigation or for drinking or for energy production? So this is really what this is about. And the last one is the climate interventions, really understanding the knowledge gaps and the risks, maybe also the benefit of anything like climate interventions. And so this is really what we do for these lighthouse activities together with the core project. And last not least, we have actually something that's called the WCRP Academy. It's an activity, a global hub, if you want, so really for climate information, for climate education, for the capacity building is always kind of a funny word. Some people also said we have capacity, we want to expand it, so it would be capacity expand. But the idea is really the educating the next generation climate researchers and training the next generation climate researchers, but also educating and informing the stakeholders about to use climate information that we have at hand. That's not always so trivial, and so we have to bring them in, we have to educate them about what the model outputs really mean and how you can use it. And that's really what this academy is about. Now, I don't have too much time to go through all the details that we do, but I do want to, first of all, inform you a little bit about the accomplishments, because if you know the accomplishments that we did over the last time, you also understand what we do. And so the first thing is we really developed and improved the observing system. I mentioned that already. The methods of detection of climate change signals relative to natural variability. That means we call this detection attribution. It's really looking at extremes or events like your hurricane that came in, and trying to understand, is that a natural phenomenon that could have happened anyway, or is that already a human-made change in the system that we might get more in the future? Advanced higher resolution modeling, really getting to higher and higher resolution modeling, improving the models, progress in representing human interventions in the land surface and water cycles, really looking into what the land surface change will do and how this impact the system. And one prominent example is, for instance, the changes in the Amazon. Basically, if we burn more and more Amazon forests, when will then actually be in a system that affects the entire global atmospheric circulation, or when will it be irreversible? And that's what we also call a regional tipping point, where the system suddenly gets into a savanna or something else and will never come back into the tropical forest. New techniques in paleo reconstruction. Paleo is actually information from corals, from tree rings, from other things, where we basically use that to reconstruct the temperatures over the last 100 years or hundreds of years. And so that's where we actually learn from past temperature changes what the system could do in principle. We had progress in advancing in changes in the Earth system energy budget, and really trying to figure out how is the temperature changing, how does this actually impact the outer top of the atmosphere, radiative interaction, carbon cycle feedbacks under changing climate, really understanding the carbon system, the carbon circulation, the cycle of it, and how this is changing. But it turns out that we understand something about the carbon sinks on land by, for instance, growing trees. Other things, we understand something about the sink of carbon in the ocean, but there are also big gaps that we know. Model data fusion techniques, we call this also assimilation, where we really made progress already. And then efforts are underway to produce global data sets, the analyses, and really merging data. So a lot of progress in this sense, and in the sense of process understanding, improve understanding of the dynamics in both atmosphere and ocean, irreversible changes in the system. And then the research-based climate forecasting, where we improve the forecasting to longer and longer timescales. There's things like what we call feedbacks in the system, clear sky feedbacks on the global climate. We better understand this now, but we also realize that there are really processes that we do not understand, or where we don't know if that actually might change the feedbacks. And then the last point here is the progress in understanding characteristics and changes in the extreme events. And so we made progress in this sense, but we also realized that we really have trouble in predicting the extreme events. And so there is accomplishments, there is progress, but at the same time, the further you get along, the more questions you will actually raise. And one of the things that the World Climate Research Program is doing, we do coordinate the science, but we also occasionally organize big conferences. In fact, every 10 years we have a really big conference to understand where we are and what the next problems are. And the last conference of this type was in Kigali in Rwanda last October. And during this conference, we identified really the challenges that are ahead of us. And I will quickly go through this and then come a little bit to a little bit more details, and the time is running, so I cannot get into all the details and maybe just focus here on the bold aspects, but just to give you a feeling where we really have to improve. The first one is observations. So one thing is really sustained climate observations. If you want to measure 100-year trends, you have to measure 500 years. You cannot actually infer a 100-year trend from just 10 years of data. And so we really have to work on long time series, on long observations, if you want to understand the climate system. The model have biases. We basically know this. The models have errors, and we have to improve these. Higher resolution, but also merge these with observations to improve these further. The system has regional variability, and it also will change more in the future. And so really understanding this in the atmosphere, in the ocean, understanding how the atmospheric circulation will look like in a 4-degree world. It will not be the same atmospheric circulation. With a different atmospheric circulation, we will have a different ocean circulation. And so these are really the things we have to understand. Earth system interactions, there are non-linearities. You cannot just think of, if I add this, this will be just also added somewhere else. You might in fact get steps, you might get catastrophic events suddenly, and you really have to understand it. So there are many things. By the way, this one is the global temperature over the last years. Each of these bars is 1 year, the global temperature. You clearly see the increase. That was the year 2023. And we have to admit we don't understand why we have this step. There's nothing in the forcing that created this. So this is one of these non-linearities I was referring to, that the system itself suddenly actually jumps and creates something, but it's not related to, in fact, sort of forcing from outside, and the CO2 is some of the forcing we relate to. So just to give you a feeling where we are working on, there are human interaction with the climate system, and one is the global cycle of energy and carbon. We are causing energy changes, but then you have changes with clouds. And so there, in a warmer atmosphere, you have more water vapor, you have more clouds. The cloud feedback, we all call it albedo, there's radiation back into the atmosphere, into the outer space. There's actually radiation back towards the Earth in terms of infrared radiation. So there's a lot of feedbacks in the system, and the clouds can be a very important aspect that we don't understand yet. Water cycle. There's a very strong interference of humans with the water cycle. Since many years, we basically use the water. We have lakes, we have dams, we have many things. We actually bring water from one region into the other. And that's actually something we have to better understand. Also how the rain will change, the interaction of climate change with human influence. So a lot of these things we have to understand. And then it comes to human interaction with the climate system, the impacts of this. Sea level is one, ecosystem changes, food security, water availability, human health, how is the climate change, also through water, through bad quality water in impacting human health. So these are all aspects that really sort of downstream in some sense of the basic knowledge that we created before. Mitigation scenarios, including overshoots and climate interventions. Overshoots is, for instance, if you want to have a 1.5 degree limit, but for some time we get over this maybe to 2 degrees and we want to come back again, how is the system actually reacting once you go from maybe 3 degrees back to 1.5 degree or less? It's actually a question really, how's the convection in the ocean changing? How are other things changing? These are all really questions that we need to investigate, and that includes land surface change, use. How is that, in fact, if you cut down the Amazon, how is that affecting the evaporation and then the atmospheric circulation? These are all things we have to understand. And last but not least, co-produced climate services and solution. All this, if you really want to make that actionable and useful, you have to understand the local context, because, as I said, the risk is different in South America than in Africa. You have to understand the community needs, the context in which a community lives. And so really producing this climate service and solutions, it has to be for local communities. It has to be on the city scale or even smaller. Open science. We deal with a global society. We deal with really a global north and global south. Open science means that the information has to be available for all. That means that the data have to be shared with everybody and accessible, as well as the climate predictions and many other things. So this also means that we have to develop the infrastructure. For instance, if you have a data center in the global north sitting where everybody from around the world can access, produce something, bring it home. These are all aspects we have to deal with. And then co-production, as I said before, if solutions should come out, you have to do this with the stakeholder. You have to do this with the community that needs that information. You have to work together and define the thing. So these are really identified as the frontiers for the science, climate science into the future. And in principle, I can go now into all the details. I don't have the time, but the essential frontiers really for the climate science for the next 10 years are in these slides. The only thing I want to add very briefly is really this need for system understanding, and that's where the 2023 comes in. As I said, we don't understand why this happened, and so it really comes back to the fact that we have a lot of interactions in the system. There could be cloud feedbacks, there could be other feedbacks really leading to this. And understanding these interactions and the non-linearities is really crucial, and that includes also understanding how the circulation in the different system works. And then again, the tipping points, we might actually come into a situation where suddenly the system flips from one climate into something else, and that's really what we have to understand, and also from where this is being triggered. That leads us into the regional tipping points. I mentioned that the Amazon already. It's actually a very prominent tipping point that is being discussed more and more. And yeah, these are really the system understanding, not just individual, not just the ocean, not just the atmosphere, the coupled phenomena. That's one thing I wanted to mention. Very briefly, the models have biases. We know this. The models cannot produce what we observe on a regional scale. That's the Atlantic heat wave in last year that we observed it. We cannot model it in the same way, but we still have to understand it. What you see here is actually the typical sea level pressure distribution. We basically, in the atmosphere, we basically have highs and lows, and the gradients typically produce the wind. If you have a gradient in pressure on the rotating Earth, you get a wind. This is what June 2023 looked like. This is actually the typical June climatology, and you basically see that last summer had a very unusual atmosphere. And so if you want to understand the ocean heating, you have to understand the atmosphere and the forcing, and including the mixing and everything in the ocean, that just to give you a feeling about this system understanding. You cannot just understand one or the other, you have to bring this together. The last point I want to come back to is the water cycle. And Tim, if you allow me 5 more minutes. The water cycle is changing. But the water problem is not just one thing, either too little or too much. I mean, too much actually can be worse than too little, as we have seen with many flooding events in Europe recently. And we really have to understand it from all aspects. There's sea level rise, which is a water problem, but if you actually have a sinking city, you have a problem from the other side where the rivers come and flood your city from actually with fresh water instead of the ocean coming in. So you have many aspects of water, and we have to realize that with the climate change, the prediction is that in 2030, 85% of the world population will live in arid regions. That means dry regions. That means where you have to bring in water from somewhere else to provide drinking water. And so in that sense, we really have to also come to a new culture, water culture, and we have to understand the impact of climate change on the water security and availability. The problem with the water is that first of all, we have to understand all these aspects, but it's also, and you will not be able to see all these details in this graphic, but it's really the most recent illustration of what changes water. And in the past, we dealt only with the physical aspects, evaporation, precipitation, raining, and atmospheric transport. But if you would look into this figure in detail, there's actually a lot of humans in here. There are cities, there's pumping out water, there's in fact irrigation, there are lakes, and then you have a lot of, and this is all groundwater. There's actually a lot of water. We have about 1/3 of the interaction between land, water, and the ocean goes through the ground. 1/3, that's actually a lot flowing, and we have no idea how that flowing goes. It implies that if you actually have a well and you pump out all your water, which people do in mega cities because they have water, and they, by doing so, Tokyo, by the way, did sink by 4 meters because people pumped out the water. we have no idea how this water comes back. It might take 1,000 years for the water to come back. And so these are all aspects we have to understand also if it comes to water security. Humans actually interacted with the water system for a long time. Irrigation, lake building, and so forth. We know the water cycle is really in the transition. These are actually the same mountain, the same glacier, 1935, and then 2022, that's kind of today, and that was, a couple of decades ago. And so the entire system is in the transition to the point that in the past we have the Himalayan, the Alps. I'm not sure where this in New Zealand, where the water storage is, that you have the water in the summertime that from the snow that was falling in wintertime. So it is unclear if the mountains will remain the water towers in the future, and we have to understand that, including glaciers. The glaciers might disappear. That's really a lot of research, and I said our GPEX experiment will deal with this. I will jump over a couple of slides here, including climate interventions, and just come back to my ending. If it comes to really what do we need to do? We have to deliver climate predictions, climate information. And to some extent, that remains one of the grandest challenges in climate science, that we really deliver accurate climate predictions, climate information, and that really requires a transition to a full range of science and humanities. At the end, if we want to do this correctly, also on the city scale, we really have to bring people into our models and into how we do this. People are part of our climate system, we call this, and also the Earth system, where the entire carbon cycle is built in, the biology is built in, and humans. And once we have this, we will be able, and we want to actually improve our risk projections. That's still a big challenge. We want to actually need to understand how these risk projections interfere or compete with other pressures, like conflicts on the Earth. Climate change is not the only problem for humans on the Earth, and that's something we have to address. How is society adjusting in a state where you have a war in Europe or somewhere else? What is the first priority that you have to solve? But I bet if we are in a 4-degree world, 4-degree warmer world, climate change, the problems will be paramount. They will be really big. And at some point, we have to deal with the problem, if we want to or not. And then, of course, we have to deal with climate justice, and the fact that the global south is affected mostly by already today, it's also very expensive for some of these communities to react, partly because they are so much in debt. And so this problem of climate justice really is something we have to deal with, and if we want to come to solutions. Tim, I will stop here. I will not get through the Kigali Declaration results, but maybe my last slide, and that's again a funny font, but coming back to the question why I'm here, it's of course informing about WCRP and what it does, but also learning, in fact, from New Zealand. That's the New Zealand scientists, but also the decision makers. What we do, what can be helpful for New Zealand by increasing the interaction with the World Climate Research Program. But also, what are the problems? I listed to you many problems, but there might be something that where New Zealand has a different problem or an addition problem, when we want to hear about these problems. New Zealand might have a problem that is very close to Brazil or some other nations, and we want to deal it with together. And that's where an interaction with the individual communities is very important from a WCRP point of view. And so that's also one of the points, and that's one of the goals, really getting into a communication, into an interaction with each other. And I think that the afternoon was already fantastic for this, for learning. and we will continue this dialogue. Thank you, Tim.
The closing karakia that I do now will take us from the stars to the land to life itself. So with that, please join me to commune in whatever way you'd like to commune. Actually, you can say this after me. How's that? Yep. Yeah. Matariki te tipua. Matariki te tawhito. Tau mai te wairua. Mai ngā ira atua. Ki te ira tangata. Ti hei mauri ora. In English, you don't need to repeat. Matariki the sacred, Matariki the old. Welcome the spirit, welcome the life force from the essence of atua to us of the humankind. Let there be life, let there be life. Ti hei mauri ora, kia ora.